What if I told you that a new groundbreaking machine has been developed? One that can print a fully functional electric motor in a very short time using a single continuous build process. Sounds impossible, right? For over a century, manufacturing electric motors has required specialized factories filled with precision tooling, laminated steel stacks, copper windings, assembly lines, and multiple post-processing stages. Building even a small motor has never been simple. But now, researchers at the Massachusetts Institute of Technology have built something radically different. They've developed a multi-material 3D printing platform capable of fabricating an electric linear motor in a matter of hours. Not a plastic mock-up, not a non-functional prototype, a real motor with conductive paths and magnetic materials integrated into a single printed structure. You will be surprised to know that the researchers estimate total material costs would be about 50 cents per device while reducing production time significantly. The motor was printed in roughly 3 hours. It required only one post-processing step. And in testing, it performed as well as, and in some cases better than, comparable systems that rely on far more complex fabrication techniques. MIT's proof of concept has the potential to change the manufacturing world. And yet, almost nobody is talking about it. In this video, we're going to unpack how this system works, what technical advantages this platform brings to the table, where its limitations still lie, and what the future could look like. Because this story isn't just about one printed motor, it may be about rethinking how hardware itself is manufactured. Stick around, because what you're about to see could be the next big shift in manufacturing electric machines. Before we start, do not forget to like this video and subscribe to our channel. Firstly, to understand how radical this is, let's briefly revisit how electric motors are traditionally manufactured. For decades, motor production has required stamping thin sheets of electrical steel, stacking them into cores, winding copper coils with extreme precision, inserting magnets, mounting bearings, and assembling everything in multiple stages. Each step demands specialized equipment and often separate facilities. The system works extremely well for large-scale production, but it is rigid, centralized, and difficult to adapt quickly. That's why printing a motor in one continuous process challenges more than just technique. It challenges an entire industrial philosophy. Now let's talk about the MIT machine itself. Instead of adapting materials to fit a conventional printer, the MIT team redesigned the printing platform from the ground up. They equipped it with 4 independent extrusion tools, each capable of processing a different type of functional material. Some materials are deposited as heated filaments. Others are extruded as pressure-driven conductive inks. Magnetic composites are handled through a separate optimized extrusion system. The printer automatically switches between these tools during fabrication. Advanced sensors and a custom control framework ensure that each material is placed with high precision. This alignment is critical because in electric machines, even a small positional error between conductive and magnetic components can dramatically reduce performance. Using this system, the researchers printed a fully functional linear motor in about 3 hours. The motor required only one post-processing step, which was magnetizing the hard magnetic material after printing. Once magnetized, the device operated as intended, producing straight-line motion comparable to conventionally manufactured linear motors. Now let's look at the advantages of this approach. One major benefit is speed. Traditional motor fabrication involves multiple sequential steps, sometimes across different facilities. This platform compresses much of that complexity into a single automated process, dramatically reducing production time. Another advantage is material efficiency. Additive manufacturing deposits material only where needed, reducing waste compared to subtractive processes like machining or stamping. The estimated raw material cost of about 50 cents per motor highlights how efficient this method can be at small scale. Design flexibility is another key benefit. Because the motor is built layer by layer, engineers are not limited to traditional geometries constrained by winding and lamination techniques. Conductive pathways, magnetic layouts, and structural components can be customized in ways that are difficult or impossible using conventional manufacturing. There is also the possibility of distributed manufacturing. Instead of relying entirely on centralized factories and global shipping networks, facilities could potentially fabricate certain motors or actuators locally using digital design files. That could reduce downtime and increase resilience in supply chains. However, this technology also faces significant challenges. Printed conductive materials typically have higher electrical resistance than bulk copper. That can reduce efficiency, especially in high-power applications. Magnetic composites used in additive processes may not yet match the performance of traditional laminated electrical steel. Scaling is another concern. Printing a compact linear motor in 3 hours is impressive, but producing larger industrial motors would increase print time and introduce additional thermal and mechanical challenges. Reliability over long-term operation is still an open question. Conventional motors benefit from decades of field data and proven durability. Printed multimaterial systems will need extensive testing before they can be trusted in critical environments. There's also the fact that the magnetization step still occurs after printing. While minimal, it means the process is not yet fully integrated into a single, seamless operation. Now let's answer the most important question. Will this new technology replace traditional motor manufacturing? In the near future, the answer is no. Conventional motor production is highly optimized, cost-effective at scale, and backed by decades of reliability data. Bulk copper windings and laminated electrical steel still offer superior electrical and magnetic performance, especially for high-power industrial applications. Large factories can produce motors in massive volumes with consistent quality and low unit cost. But replacement isn't the only measure of success. This MIT platform could excel in areas where traditional manufacturing struggles, such as rapid prototyping, low-volume customization, research environments, or remote locations where supply chains are slow or unreliable. In those cases, the ability to print a functional motor in hours could be more valuable than achieving maximum efficiency. So rather than replacing traditional manufacturing, this technology may complement it. Mass production will likely remain dominant, while multi-material 3D printing opens new possibilities in flexibility, speed, and distributed production. So what does the future look like? The research team aims to integrate magnetization directly into the printing process and explore the fabrication of fully 3D printed rotary motors, not just linear ones. They are also working on expanding the platform to handle more materials and more complex electronic architectures. If successful, this could open the door to printing not just motors, but entire electromechanical systems in one coordinated build. Imagine robotic actuators, customized medical devices, or integrated sensor motor assemblies produced in localized facilities. The boundary between electronics manufacturing and mechanical manufacturing could begin to blur. We are still in the early stages. This is a proof of concept, not a mass market replacement for industrial motor factories. But it demonstrates something powerful. Complex electric machines can be fabricated additively with meaningful performance. And sometimes, technological revolutions begin exactly like this, quietly in research labs before the broader world realizes their potential. So here's the big question. If motors can be printed in hours, if hardware can become digital and locally manufactured, what happens to traditional supply chains? What happens to spare parts logistics? And how might this reshape the future of industrial production? Let me know your thoughts in the comments. If you enjoyed this deep dive into emerging engineering breakthroughs, make sure to like this video and subscribe to our channel for more content, exploring the technologies that could define the next generation of manufacturing.